So we'll start with our Friday resurgence and non-perturbative methods session. And we're very happy to have Veronica Fantini talking about strong weak resurgence and L functions.
Thank you very much for the invitation, and I would like to thank the organizer of this session. Today I will tell you about part of a joint project with Claudia Rella. And so as you might expect, talking about strong and weak in a conference on string theory would be reflect to the limit in the string coupling constant GS. But more precisely for today, I will consider limit in this H bar parameter that is still related to the string coupling constant in a sort of dual way. So strong will reflect to the limit at infinity and weak to the limit at 0. And more precisely, I will be working in the context of the topological string spectral theory correspondence. And in fact, I will be considering the so-called first fermionic spectral trace in the example of local P2. So among the two sides of the correspondence, I will work on the spectral theory side. And the heart of the what we call a strong-weak resurgent symmetry is capturing a sort of duality and relationship between the perturbative and non-perturbative contribution in the two regimes. But what I think is really beautiful in the story, maybe this picture, but this is not what I did, is the fact that we can describe this relationship between perturbative and non-perturbative contribution in the language of L function, and it's really captured by an equation which is called the functional equation, which tells you how to do the analytic continuation of a certain L function, which captured the Stokes constant in one regime, and the L function which captured the Stokes constant in the other regime. So that's somehow the idea. And to begin with, I will start with a very quick introduction about resurgence. It will be really one slide, because we have heard a bit about it also on Monday. And then I will also be very quickly in describing what is the framework of the topological string spectral theory correspondence. And I will try to dedicate more time in explaining essentially what's the model, what the example of local P2 look like, and which type of resurgent structure we see. And please interrupt me if you have any question. So the theory of resurgence has been introduced in the 80s by Ekal, and is the theory that studies divergent power series. In particular, to a divergent power series that will be denoted as an element in this formal power series Y, it associates what we call the resurgent structure, which is the data of a set of singularity in the so-called Borel plane, so in the complex plane, the Stokes constant, which are attached to each singularity, and some new germ of formal power series, of analytic function which resurge at the singularity. So why do we care about this type of data? Well, because it's precisely what allows us to compute the so-called non-perturbative correction. These are exponentially small corrections, and in fact they always appear in the following form. So in particular, you see that the position of the singularity in the Borel plane is what will be described this exponentially small correction. And then you will have the position, the Stokes constant appearing in front, and this new power series here, which a priori is formal, it's related to this germ of analytic function through a Borel transform. But as you might already know, divergent power series can arise in many different contexts. But for today, we will look at divergent power series that arise by taking the asymptotic expansion of a given analytic function. So in a sense, we have already an analytic function, and we look at the asymptotic expansion. This will happen to be divergent, and we will be interested in studying their resurgent structure. So where does the function I'm interested in come from? That's precisely in the context of the TSST correspondence that goes back to many works of these people, and maybe one of the first one was the work of Gracia Sudamarino from 14, but he relies on different collaboration between them. And so there are two sides of the correspondence. Let me start from the topological string side. So here, the starting point is to consider a type 2A topological string on a Calabi-Yau threefold, which is non-compact. So in particular toric threefold, and in a while it became local P2 for my example. And what the quantity we are interested in is the so-called total ground potential. So this is defined, contains two contributions. On the one hand, what is called the worksheet ground potential, which essentially capture already at the non-perturbative level the Gopa-Kumaba invariant. And the other contribution is what is called WKB ground potential. This conversely capture, it's expressed in terms of derivative of the refined topological string, but in the NS limit. As I said, this is in a sense already a non-perturbative completion of the topological string on X. And what the TSST correspondence is telling us when we go to the spectral theory side is that in fact we can relate this object with some quantum mechanical operator that arise on the other side of the correspondence. And so this is how we consider, so how they consider, they define the spectral theory side. So the first thing is, since we are in this toric setup, so the Calabi non-compact, we can describe the mirror curve easily by as a curve in C star square. So this is in fact in a sense capture the mirror of the Calabi-Yau. And this function here is precisely the one we are going to quantize to introduce a certain operator. And the parameter that you see here is a parameter in the complex moduli space of the mirror of X. Now the quantity of interest is what is called the n-fermionic spectral trace. So as I said, they arise from the quantization of this function O simply by essentially using the standard Weil quantization and promoting the variable x and y to operator. And so in particular, we satisfy the following commutation relation where you see the appearance of the H bar. And this is an operator acting on L2 of R. Now, it is not a trace class, so in particular, the quantity to be considered is the inverse of this operator, and then the so-called Fredholm determinant. Now, the trace appear at the expansion as at kappa equal to 0, and they are the coefficient. So importantly, this quantity here is entire in kappa and analytic in H bar. And so again, we have all these coefficients will be analytic function in H bar. And what the TSST correspondence predict, at least in one of the formalization that uses the traces, is the following. So you see here the relation between the nth fermionic spectral trace on this side and the total ground potential which appear here at the exponential. And the relation between this parameter mu and the kappa that appears here is the following. So what is the advantage of this formalization is that, well, now we will be interested in study the asymptotic expansion of the trace, and remarkably, it doesn't depend on the parameter kappa, which is a parameter on the moduli space. So from the point of view of resurgence, dealing with at a fixed n with this type of object is much easier. And what this equality should tell us is that looking at the limit h bar to 0 or infinity, in a sense should be related to what the total single potential is also capturing in the respectively regime. Now, the resurgent structure of these fermionic spectral traces has been discussed and studied by J. Gu and Marino and by Claudia in both the h bar 0 limit, h bar infinity. And so far is mostly conjecture, but we have example in which in fact we can do computation exactly, that's precisely local P2 as I will describe. But at the same time there are also numerical evidence, for instance for local F0. And so the idea is that we will consider the logarithm of the trace at fixed n in the two regimes that will give rise to two formal power series, psi and phi, so respectively in the inverse h bar or positive h bar, positive power of h bar. Both series are conjecturally resurgent and of type Gevrey 1, meaning that the coefficient grow factorially fast. The resurgent structure should be given by a so-called peacock pattern of singularity. So here you see a sort of cartoon. The idea is that the singularity in the Borel plane are displayed in this tower. And so what I'm drawing here with this other line are where the Stokes line are. So you have to imagine that each of these points is a singularity of the Borel transform of this function. And again, what is very interesting also from a geometric perspective is that the Stokes constant that appear for each singularity should have a geometric interpretation, possibly in terms of some enumerative invariant which are captured by the geometry of the problem. And in terms of this geometric interpretation, there have been conjectured by Gu and Marigno, mostly in the limit h bar to infinity. Okay, so that's somehow what we know in a quite generality, what it is expected. And I will now try to describe what we studied in the example of local P2. In particular, we focus on the first fermionic spectral trace, so n equal to 1 in the example of local P2. And thanks to the previous work of Claudia, we in fact know that the resurgent structure is very simple in that case. In particular, she also managed to get exact computation of the Stokes constant, the position of the singularity, so everything is known explicitly. And thanks to that, we also can see very nice arithmetic property. Now, building on this result, what we come up with is to understand somehow that there is another way to describe the resurgent structure of this function comparing the two limits, and this is very quickly summarized in the following diagram that we will see a little bit better later on. So the idea is really that looking at the perturbative expansion of this function in the limit h bar to 0, what will be appear here, we can look at certain structure and find out that the non-perturbative completion of this expansion are in fact do in fact capture the so-called perturbative expansion in the dual limit, and you can close, and then you can close the diagram. So there is an exchange of information between the perturbative expansion in one limit and what captured the perturbative expansion in the other limit. And to do that, you can rely on some resurgence technique, but as we will see, there is also a very natural mathematical way and that connect these two parts of the diagram. Okay, so that's a quick overview, and now let me tell you in more detail what the resurgent structure of local P2 is, and then I will try to make precise the previous picture. So this part of the talk, in fact, relies on the previous work of Claudia. And so to begin with, what is local P2? You might know this is the total space of the canonical bundle of P2. And the mirror curve of this function is exactly what you see here. After you remove, after you change back this xy in the not math SF character. But so in particular, after we quantize the mirror curve according to what I was writing before, the operator look like that. And as computed by Kashaev and Marigno, the first fermionic spectral trace has this very explicit formula. So you can see it first as an integral expression where the two Fadev logarithm appear. In particular, this is analytic in this h bar coordinate, which is defined on the complex plane minus the positive real. And you can actually rewrite this integral in a much nicer expression in which you see the Q-Pochhammer symbol. Now, here there are 4 of them. In particular, you see what I call antilomorphic block as this Q tilde variable. So Q tilde, now here there are a bit of different variable, is essentially in 1 over h bar. And the Q variable is in positive h bar. So in particular, they will contribute respectively in the asymptotic expansion h bar to 0 or h bar to infinity, respectively. Okay, so that's the structure of the trace. And now, as I said, looking at the asymptotic expansion of the logarithm of the trace, you get some very similar structure. So let me just go through the resurgent structure of the asymptotic expansion in the limit h bar to 0, so in the weak regime. This is a rational function. This one here is, just to remember, is Gevrey 1. It has a tower of, its Borel transform as a tower of singularity, which are spaced by this quantity, which I call A naught, 4 pi square over 3. So this is kind of an example of the peacock pattern I will show you before, but there is only one tower. And most importantly, the Stokes constant attached to each point are known in this explicit formula. So this is just a divisor sum function, and they are, after this normalization, they are rational number.
Sorry, Veronica. This is for n equal to 1?
Yes.
So if you do n equal to 2 and higher, you start getting more.
The more, yes. In the work of J. Gu and Marcos, they did it in the limit h bar to infinity, and you see the second tower of singularity. Okay, and similarly, if you look at the resurgent structure in the other limit, so h bar to infinity, that here for convenience became a tau, so tau to 0. Again, you get a single tower of singularity. Now the space between the singularities is given by this A infinity, and once again the Stokes constant has this very simple expression. Now, in order to capture the non-perturbative correction, so what we usually do in resurgence is to look at the so-called discontinuity. That is essentially what captures the subleading order contribution, as you can see from this exponential here, which, since we only have simple pole in this example, is nothing but a residue computation when you take the difference between two Laplace transforma along this line. And so you see that, in fact, the Stokes constant appears as coefficient, and remember phi was the h bar to 0 limit, so you see exponentially small in h bar. And now, remarkably, this function, in fact, thanks to the fact that we know the Stokes constant explicitly, can be written again as a ratio of two Pochhammer symbol. These zeta 3 and zeta 3 2 are the third root of unity and their square. And this, now you see the Q tilde series precisely because you have power, inverse power of h bar. But in particular, this is very closely related to the logarithm, to the anti-holomorphic block of the logarithm of the trace. And very similarly in the other example, so for the h bar to infinity limit. This, in a sense, is a sort of first instance of this strong weak resurgent symmetry, because phi was the perturbative expansion in the weak regime, and after looking at the non-perturbative completion, we find the block that, in fact, will be giving the asymptotic expansion in the other regime, and vice versa. But that's not the full part of the story, because in fact there is another way you can encode the Stokes constant, and this is precisely what the L function are doing. So you can introduce this the L function, let's say L naught, which is whose coefficient are the Stokes constant in the weak coupling regime. Again, you know the Stokes constant explicitly, so you can see that this L function is a product of the Riemann zeta function and the Dirichlet L function with respect to this character, shifted by a 1, and similarly in the other regime. And if you compare, again, the two L functions, they are not really different. There is a different shift in S, so here it's in the Dirichlet L function, and here is in the Riemann zeta. But they're kind of closely related. And, this, and as we will see later on, in fact, they are related, and they also capture this strong weak symmetry. Okay, so what is this strong weak symmetry about? Let me just start with a diagram which summarizes what I just showed you as a first instance of the strong weak, so the really resurgence paradigm. So if you start like on this corner where you have the asymptotic expansion in the weak coupling regime of the logarithm of the first fermionic trace, so by resurgence you first compute the Stokes constant and the singularity, and then by computing the discontinuity on the generating series, you find what we call the strong, because it's precisely what captures the asymptotic expansion in the other block. So from here, if you expand that tau goes to 0, you recover precisely the other series, and then you can close the diagram. So in a sense, going from this asymptotic expansion to this discontinuity is really the standard procedure in resurgence. What I found kind of interesting and relevant in this story is that you can really close the diagram, so that already from the beginning, essentially, the fermionic trace knows about both regime. And so this is like a first way to think about it, but in fact, in a certain sense, you can even kind of forget about the connection between the two and just go vertically. And go vertically by using certain transformations, such as the Mellin transform that we saw also this morning. And once you get the L function together with this A infinity, you can recover the other asymptotic expansion. So you can go both ways, and that's precisely what the strong weak symmetry is about. It's related to resurgence if you think to the other type of the diagram, but in fact, it's purely mathematical in a certain sense, and it's a consequence of this type of transformation you can have. And here I did on purpose that these H bar and tau are kind of a bit less colored, because in fact, the strong weak is purely at this level. If I want to connect the two limits, this is where the functional equation for the L function come into play, because in fact each of these L function is only defined an analytic on a half plane, but you can compute the analytic continuation, and after you define this function lambda 0 or lambda s by adding some gamma factor, you get this very simple equation where you have that essentially the analytic continuation of the L function in the weak regime is given in terms of the L function in the other regime. That is also quite surprising also from a mathematical point of view, because for instance, if you have seen L function before, like the Riemann zeta function, typically you have the same on both sides, so you don't see two different regimes in a sense, or two different L functions.
There are, so since you're dealing with a divisional character, there are indeed L functional equations which mix different characters.
Yeah, typically, these one are...
they're real, right?
Yeah, they're real.
They expect to be the same.
Yes, that's why. Okay, and so in particular, if you use this functional equation, is what tells you how to connect the two regimes. So it's really in the functional equation that you can see this duality in a certain sense. And moreover, the functional equation also precisely governs what is written here in terms of this transformation. So you can read the diagram in many different ways. You can start from the node, the one you like the most, and you can move and recover all the information. So here I put this slide to tell you how the functional equation really compute, it allows to move from the two sides of the tower. I don't want to go too much into the details. So the point is that you start with if you start with a series in the following form, so from let's say the non-perturbative expansion, essentially you can compute the asymptotic by expanding the exponential. This will give you an L0 with minus k, so the L function but with the negative integer power, evaluated at negative integer. And if you want to make sense of this, you have to use the functional equation. And if you do that, since the functional equation knows about the other regime, you will get the L infinity, so precisely what capture the asymptotic expansion in the strong coupling regime. But okay, so let me quickly summarize what I discussed so far. So this strong weak resurgent symmetry is really about the interplay that you have between the two regimes. So, and both how the perturbative and non-perturbative contribution talk to each other. I think it's quite remarkable that in a sense you can close this diagram with using these techniques. And in particular, what I really find fascinating is that the functional equation, it's really at the heart, because if you start from there, you can really move everywhere else, and this is quite elegant also in a certain sense, because it's quite simple, and you see both regime in there. Now, more generally, after this, one would like to maybe see even more what are the structure and what can we say in terms of this L function that we find, and so on. So one of the other results that we discuss in the paper is that, in fact, if you are familiar maybe with the usual modular form, one natural thing is that, okay, after I take the Mellin transform, I would expect to get something maybe modular. That's not the case. In this example, if you take the Mellin transform, and so in particular, if you look at the discontinuity, these turn out to be quantum modular form. And if you have never heard about them, they're not really modular. It's precisely the other way around. It's something that breaks modularity. It's not modular invariant, but it's very interesting in any way. I mean, the appearance of this quantum modular form is also interesting in this context because they are objects that appear quite often in Chern-Simon theory, so it might be interesting to understand better if there is the relationship, if there is a deeper relation between the two. Thanks to this formalism that we introduce, which is in terms of L function and the functional equation, we can in fact generalize somehow the resurgent paradigm, the usual resurgent paradigm, and introducing what we call modular resurgent paradigm. This is precisely the same picture I showed you before, but where you can forget about the fact that you start with the fermionic spectral tracer or something that has naturally a strong weak symmetry. The same type of structure can be observed in much more general situation. And this is part of a companion paper. Okay. and very quickly, so like other question that one can ask in terms of this strong weak symmetry and that we would like to understand better is first if we can go beyond the example of local P2. This is kind of the easiest one, but it will be nice to look at other example. Local F0 will be the most relevant one, but maybe a bit harder for the moment. And finally, it will be, I think, also interesting to see whether this strong weak resurgent symmetry holds for the full spectrum determinant, so where you have back this kappa parameter. And yeah, that's one I want to finish. Thank you very much for the attention.
We have time for a couple of questions, extra questions. Anyone?
Thank you for the nice talk. So I have a naive question since I'm not expert in this field. So you showed that in this case of the local P2, there is a very rich structure and with many beautiful things. And you hinted that for the local F0, it's already much more difficult. So my question is, can you give me some understanding of why this example is simple and other toric Calabi-Yaus are much more difficult? For example, I don't know, just the conifold would be a very simple case.
For the conifold, we have to take a look back to because of, in fact, where is it? Like in the original discussion by Grazia, Tsuda, Marino, it was, okay, essentially the spectral theory side was not really considered. So I think we should try to write down what this Z corresponds for the conifold, for instance. But for local F0, the integral expression is not too much complicated. You still have a ratio of Fadev. 3 is a 4, and you have this, both are squared. So the structure here, it's really similar, and that's expected also for other toric threefold. Now, if you want to do the resurgence analysis, it's much nicer to have it in this form. For local F0, the form that Claudia considered was the one first computed by Marcos and G, but it's not so nice. So you don't have the Q-Pocamer symbol, it looks a bit more complicated. Honestly, I think that maybe working a little bit harder, I hope we can write it in terms of Q-Pocamer. But the way we didn't tackle that problem first is because the formula that was given for free was not in terms of Q-Pocamer, and so it became much harder even from the numerical point of view to extract the Stokes constant and so on.
And for the weighted projective space, instead you can do that?
Yes, for that we have it's really very similar to that.
Okay.
Yes.
Thank you.
One more quick question.
Hi, sorry. In this diagram that you had this arrow that at some point becomes light gray, the horizontal one. Just to At the technical level, what is this arrow? So is the asymptotic series that you get in the discontinuity, so the asymptotic series of the discontinuity is just this?
Yes.
So you don't have to re-expand anything, just, okay.
Yeah, exactly.
So I think we should try and go for the sake of time, but thank you for the beautiful talk. Thank you.